modeling isn't going to be accurate. The concept of friction isn't really meaningful unless you have a spatial separation between the surface properties and the spatial frequencies of the objects you're manipulating. And in soft robots, we don't have that separation. That the approach of just learn a policy is going to win. And systems with a library of such policies that can recognize when to use them are going to outperform model-based approaches.
And
that's a challenge rather than a question.
Yeah, and it won't produce a good discussion here because I agree with you.
That is so disappointing.
Yeah, but let me explain where I agree and where I don't. So I think you're right. Most of our models talk about state. Russ Hedrick talks about this, that we do state estimation, we plug states into models, we get interesting and useful predictions. What is the state of a pile of rice? It's just not possible. You chop up an onion and you change it from a rigid, quasi-rigid sphere to 10,000 little tiny pieces of onion. Good luck with that using a model. I would agree. On the other hand, learning those models is particularly challenging. I don't think that's an easy model to learn. Whereas for rigid objects, and there's an awful lot of useful things you can do in the world with rigid objects or quasi-rigid objects. So it's not as if the model-based approach has to solve all these problems, but I think it can produce some pretty useful systems in the near term, frankly, with much better guarantees of performance, much better understanding of uncertainties than you can get if you just try to learn everything.
So I have a question that I meant to ask. I mean, I think I emailed also the panelists about this, which I've been thinking about. Like, what are the open challenges in the field of tactile sensing? Like, for example, like if I randomly walk into a robotics lab now, it's very easy for me to see almost all the robots will have a camera, but much fewer robots actually have a tactile sensor. Is the challenge the hardware, the modality itself, the software? What is the challenge? It'd be great to hear some thoughts on this.
First and foremost, we have to build devices that can handle tens or hundreds or even a million cycles of whatever it's supposed to be doing without breaking down. If it doesn't do that, it's not going to be widely accepted. I've been watching the development of hands for decades, and I'm stunned that we still don't have, reliable, compliant, soft, in the sense of soft skin, hands with palm degrees of freedom and stuff like that. The Utah MIT hand had a lot of amazing stuff. Salisbury's hand had a lot of amazing stuff. The Shadow hand has a lot of amazing stuff. But yeah, they weren't reliable, and they're not ready to be workhorses in the lab. And also, when people look at that complexity, their mind shuts off. So, I would say you got to have stuff that works, and you got to have a hand that works.
I was just gonna throw. Sorry if there's like a hand raise feature or something you want me to use. I can get in line. Well, let me.
It's free flowing. Feel free.
Let me just make my quick comment here. So I agree that you don't want things to break, but things will degrade over time, right? I mean, with any of these systems, whether kind of more conventional or whether these kind of soft, squishy things. I mean, you are going to get changes, degradation over time, fatigue. You're going to have to make repairs, adjustments, augmentations, right? And so I think kind of, addressing this issue of kind of non-stationarity, into whatever kind of, learning scheme or model-based scheme or whatever it is, that has to be kind of incorporated, into how these systems operate. I think there's basically no escape from having something that's going to be stationary in its function for those millions of cycles or months or years of operation.
So is the challenge? Is the challenge? Is there a common consensus on thinking that the challenge is more on the hardware side right now, because we do not have these systems that have a long life cycle, which can with physical interactions, or am I misinterpreting?
Well, I mean, my comment was actually more on the algorithmic side. I mean, I'm saying just accept the fact that the hardware is what it is, and so I would say there's still a lot of challenges kind of on the algorithmic side as well.
I think there is a question from Giorgio. Giorgio.
Yeah, I just wanted to point out that, the starting point is the hardware. I agree. But we had a long project about 10 years ago. It was called RoboSkin. And for some time, we struggled to find problems where tactile sensing was winning. I mean, so this was a continuous discovery, and we keep on inventing problems where tactile sensing is important. So there is another thing. I enjoyed the talk of Chris today, because 20 years ago we discovered CAN bus microcontrollers to start building embedded controllers for robots. And today we are now discovering cell phone technologies for developing sensors. So there is always another domain, and we inherit technologies from those domains. So robots still do not become a technological push for the development of specific technologies. So I think that we should arrive at a point where we have applications which become so important to develop hardware technologies, and at that point the evolution will speed up, certainly.
I guess arguably, if we look at humans as a model for what's possible in the space of robotic grasping and manipulation, we have plenty of examples of added value of having prehensile limbs with general manipulation skills that translate to many tasks. Try to imagine any area of that relies on human endeavor without the use of hands. Things become very challenging. So I appreciate that thought that from a practical standpoint in particular, but also in research, that it will be really helpful to have the value there because of the large investments that may be needed. But I think the history of technology also shows that devices, when they attain a certain level of functionality, the things that they are used for are actually very difficult to anticipate in advance. I'm meeting via remarkable, pocket supercomputer now with a giant screen that sees applications I think few would have anticipated before they became commodity devices, for example. But arguably the situation for robotic manipulation is a lot better in that regard, because we have good models. My thought about the original question is perhaps also that is a big myth area for where advancements and maybe different ways of thinking about problems is needed is possibly in the area of generalizable physical skills. So, if my robot has attained some basic proficiency, perhaps it's not immediately able to dice a carrot, the way a top chef would like, but with less than millions of iterations of training can, hopefully learn to do so, or you could probably come up with better examples than that. But accepting that there may be some need for modeling and data-driven learning of some basic skills. How can we arrive at having robot hands that are able to wield chopsticks and scissors and hammers and sort Legos and all sorts of things, reach and clutter, et cetera. Seems like an area that's difficult to address within the state of the art today.
So, Jon, I have a question. We are basically, at the moment when it comes to the perception and learning, we are using sensing, action, and learning, right? What about predictive coding? So do you think there might be a kind of a solution to use predictive coding to perceive, to have a better perception and learning?
What do you mean by predictive coding?
So in human, we are using basically predictive coding and active inference, right?
Well, I'm not a motor expert by any means on the human or robot side, but I think somehow we need to be able to understand how to address novel tasks more efficiently, right? Using the sorts of things that a hand is good at, and how do we compose motor programs in a way that yields good solutions, good abilities without tons of trial and error or levels of inference that are maybe impractical if you have a robot in the wild that needs to acquire new skills in the course of operation.
I would just say it's clear intelligent systems learn to predict what's going to happen. And we're all pretty good predictors of short-term weather. I think it's going to rain in 10 minutes. But that doesn't mean it has anything to do with our control. We're probably pretty good at predicting when policy 15 is actually going to work, but that doesn't mean we're using that prediction while we're doing policy 15.
We have, thank you very much, Jon and Chris. We have one question from Anirvan. Anirvan, are you here?
Yes.
Yeah, please.
Yeah, I think this also falls into this model-based and learning-based approach, but I think not a lot of talks talked about exploration, like few presentations were there for active exploration and active control. So I wanted to know your thoughts. Having physical and intuitive state representation is better versus self-learned deep representation for such active-based control problems. Which of them should be used to pursue research? Or do you have any insights that will be really helpful? Thank you.
So is there any question, any answer? Anyone is my PhD student, so he's searching for some feedback from you.
I think the use of latent spaces is a really good thing in machine learning, and inevitably that's something you concoct by processing a lot of data, but it's not magic, it's just statistics.
So coming back to the previous discussion, I think following up on what Carmel and Jon had mentioned, which is the other side of the challenge, the algorithmic challenge, is the challenge because, like, let's say if models are not perfect and you want to model the residuals using data-driven methods, is the challenge, especially for haptic sensing or tactile sensing or contact sensing, the lack of availability of data, and is it because you need actually physical interactions in the real world to get the data, or lack of simulators with proper physics realism? Like, what is the challenge for those on the algorithmic side or on the data side?
I just did chime in. I definitely there's a great need for data on the haptic side. The incredible advances we've seen in computer vision over the past decades really taken great advantage of the availability of common data sets and understanding how to learn from such data, how to learn between problems and things like that has been really valuable. And so I think this would certainly be a big step forward. I guess one of the difficulties is that in haptic interaction, we have a few complexities to deal with, including the action dependence of the signals that are collected, the active nature of the modality, and the difficulty of translating haptic data between different devices that may elicit very different kinds of signals, for a host of reasons. Even given common underlying sensors, things like surface hardness or surface stuff like that can dramatically alter the signals that are produced. Humidity. So those same factors make it rather difficult can make it very difficult to understand how, for example, animals or humans use these signals, because if you take the simple act of sliding a human finger across very controlled textured surfaces, the data fluctuate greatly, and it's an open question what signals are that are used by people in very simple perception tasks like surface discrimination. A lot of those same challenges would extend to robotics, or even be amplified by robotics, where the end effector is decidedly non-standard and difficult to standardize or map between in the ways that we can do with cameras or auditory sensors.
Yeah, I'll echo a lot of the same things. I mean, as Chris and Rob were saying at the beginning, I mean, a lot of these systems, especially kind of in the soft material space, are highly stochastic. So even, I mean, there's been a lot of, great progress and kind of deterministic modeling based on these, all sorts of different physics engines. And that's actually kind of a little bit more tied to my own background. But I find that it just doesn't cut it, for a lot of these cases when there's just, so much going on in terms of the heterogeneity of these systems, and just the large scale of numbers of different features. And so kind of ways to tackle that, if you do want to cut down on kind of the size of your training set or whatever, I mean, there's, nice things you can do with like transfer learning and, and so that's something that we've been, trying to kind of take advantage of in the work that I've been doing. But no, I mean, just to kind of reemphasize again, kind of, something that we've definitely been kind of facing. Another issue with these heterogeneous material systems is that they are subject to so many different influences in terms of physics, and Jan was talking about all the different environmental conditions, and that's all the more reason that we can't think of these as being kind of static mappings or having and we constantly have to kind of update and have these systems kind of relearn. I don't know enough about biological systems to know, kind of what the analogies would be, in kind of natural sensing, but that's certainly something that we're seeing increasing need for in these soft material systems.
Chris, I have a question regarding vision-based tactile. I have two issues when it comes to the vision-based tactile. One is basically we are not able to get the informations. Let me give you an example. For example, when I'm sliding my finger on a carpet, right? A carpet has the texture has a direction, right? So when I'm sliding my finger, I will get several information during the sliding, right? For example, the stiffness, the textural properties, friction coefficient, and so on, right? But when it comes to the vision-based tactile, like a gel side, I'm not getting this kind of information, right? The information is completely different. We are getting almost the picture or the picture of the texture is not let's say the tactual properties. And the other one is we cannot really scale this kind of technology. For example, now in automotive industry, when it comes to the interior, let's say the future, the seat will be kind of an adaptive, means will have some morphing features. Means the seat need to be covered with the tactile sensors, will, for example, estimate the body shape and so on. When you are moving, can follow your body, which is called a liquid interior. So how we can use vision-based tactile in order to first to get the information, tactual information, and how we can also scale it, right?
Was that directed at me? Because I'm happy to answer it. So think in terms of gel site, think in terms of videos rather than images. Wenzen Yuan is looking into sort of high frame rate gel site, and of course you can get movement descriptors. Optic flow has been around for a long time, and that will give you comparable features to a tactile sensor. Now, I would still want to measure physical vibration, microphones, accelerometers, whatever your favorite way is. So it's not that I'm saying only use vision. I would certainly use everything else I could fit in there. Interestingly, the high frequency measurements are not images. They're much larger. They have much more bigger receptive fields in the neuroscience sense, and that's probably fine. Let's see. The second part of your question was, what's it going to cost to have a lot of these cover a whole surface? In the glorious future that I imagine, cameras will be dirt cheap. They'll be printed on wallpaper or whatever, clothes, whatever. They'll be lensless and spread like peanut butter, so that you don't have to have the 1 centimeter between your camera and what you're looking at, so that the photons can move and rearrange themselves. And you'll think nothing of 1,000 camera systems. It will be cheaper to lay out cameras than it will be to lay out strain sensors or pressure sensors.
Well, a question is here, basically, when it comes to the humanoid, or let's see tactile sensing in a human, right? We are not using tactile only for the manipulation, but also for the body perception, right? Self-awareness, this is my hand, right? This is my body. So the way I'm moving my hand, if my hand will be kind of, I put it, this is like everyone knows that if you put your hand into the mixture of water and ice, then even you cannot, you don't know this is your hand, right? Means you cannot really move your hand or grasp any objects. So do you think the camera, even if you will have a cheap camera, or as you said, for example, printable camera, do you think we can get this kind of information or this kind of perception on humanoid? Because it's, okay, especially you are a fan of Bimax, right?
So you're mixing a couple things together. If you had cameras all over your body, those cameras are going to see your body parts. Just, you know, so will you be able to see yourself? Yes, you will. Will that be, so in the proprioceptive system, skin stretch plays some role. And whether you can replace skin stretch measurements with something else, you know, for example, with complicated situations like your neck and your hand, will you be able to figure out the kinematics of those things by looking at them rather than having skin stretch and joint sensors? Well, I'm certainly not throwing out the joint sensors. I'm dubious about the skin stretch sensors. I think, yeah, we can swap vision for skin stretch.
So what do you think, Carmel?
I mean, I kind of see, I mean, what I find appealing about Chris's kind of idea, his vision for kind of, you know, using vision is that, I mean, you can, I mean, by augmenting these kind of cameras with other materials, I mean, I think you can, you know, you can do more than see, right? I mean, you can also kind of detect tractions and, you know, measure strains and so I don't really see it as kind of an either or type proposition. I mean, I kind of see for free, you can actually get kind of strain sensors embedded inside, you know, if you put the right coding on that camera and are able to track kind of, you know, emotional particles or something, which is kind of what you get with the gel sight, you know, and different variations of that. So, so I don't see that as a trade-off.
Can I jump in with a response to this too? So I mean, we're talking about when is tactile sensing essential and that kind of thing. I think a better question might be, when is it the right solution? So for instance, you might say to pick up something slippery and deformable, I need to have contact sensing. And then you go to have Chinese food for lunch and you use chopsticks. And you pick up slippery, deformable foods just fine with absolutely no contact sensing. And the reason you can do that is you've got this amazing three-dimensional vision system, and you've got some amazing internal mechanical models that let you relate this sort of fine motor control you have to the way things are going to move around and deform and get them to go in your mouth where you want them to go. On the other hand, you know, the toddler at the next table is eating the Chinese food with their fingers and doing just fine. So you can do it a lot of ways, and this vision Chris has of using ubiquitous vision to do everything sounds like the right solution if it really is something you spread like peanut butter and it costs as much as peanut butter, as it is easy to program as peanut butter. But in the meantime, I think there are situations where vision makes sense as the right contact sensing modality, and other times when it's just terrible. You know, I want to reach in my pocket to get something. I don't want to put cameras and LEDs on the tips of all my fingers. I think contact sensors might be a good way to go there. So it's sorting out which is the right solution to which manipulation problem. I think says where to use tactile sensing, where to use vision.
I think this is great discussion. I know that we are pressed on time, so if I can categorize all the discussions that happen in the panel, I can think of basically in terms of open challenges. which relates to solutions. Like one, we talked about hardware, where we talked about, the complexity of building the systems and the connection with, the life cycle and everything. The other is on the software side, availability of data, transferring to different platforms and interactions. And the other is finding that killer, the set of killer, applications where tactile sensing is the right solution that motivates the field to go, right? So if I consider these three as the main, main three ways, what can we do? I would like to conclude with get some ideas of action items, like as a community. What can we do in these three directions to progress in this field, or what are the action items for us as a community should be, so that we keep our discussions focused on these three things? Any thoughts?
Our scientific style is to narrowly focus on one thing. And if you looked at the various talks today, they didn't use multimodal sensing. They typically had one sensor doing one thing. I would argue that at least some part of the community has to push as hard as possible in the other direction of let's build as complete systems as possible and see what we can do with them. And maybe this is like high energy physics, where there are big installations, particle accelerators, whatever, that have everything we can imagine, and ask the question, how do big systems work? And that's not something academics is really enthusiastic about. But if you want to answer the question, what can we do with robots? I think you have to give them a chance, give them as much as we have.
Yeah, Carmel, you had your hand raised. Yeah. And also Giorgio, I think, had his hand raised. Yeah. Feel free to just speak up. Yeah.
It's the same. Go ahead. Carmel.
No, I was going to say, I mean, early on, as a faculty, a big inspiration for me was, seeing the success of, Rob Howe's, technologies being commercialized, right? His tactile sensor. And so that for me is also kind of a template, I mean, to see what's going to make impact, just go commercialize it. And you don't have to be in Silicon Valley or Boston or kind of one of these other, big ecosystems, right? I mean, nowadays, I mean, you can, get VC money almost anywhere globally. So just get your technology out there.
Yeah, I think that is the ultimate test of how good your ideas are. Do they have application in the real world? The unfortunate thing about that is we don't really know what technologies are used. The companies who build successful robotic systems don't tell you what they're doing in there, which algorithms they're using, which sensors they're using. That's competitive advantage. So as much as commercial success is good for all of us, I'm afraid it's hard to work backwards and get the insight into what worked and what didn't work from the stuff that's out there. But let me suggest something that I've come to in decades of doing this. So starting out early on with tactile sensing, we just try new ideas. There are all sorts of new directions to go. And what about a sensor for this? Can we use it that way? And that was certainly fun. I'm not sure how much progress it made at the end of the day, but where I'm going now is I'm trying to find well-defined problems where maybe tactile sensing is the right idea, but at least I can test whether it is the right idea by saying I'm going to try to do ultra-reliable manipulation in our case, for instance, and say, can I prevent things from slipping? What's the best way to do that? And we don't know yet. It may be video. Maybe Chris is right. We need a lot of cameras everywhere. That's the smart way to do it. It's the cheap and practical way. But that focus on specific problems, I think, can move the field forward.
Yushe, yeah, you have a question? Thank you. This is really amazing discussion. Yushe, yeah, feel free to unmute yourself.
Yeah, thank you. Yeah, I want to ask a question. Actually, first, in the beginning,
we cannot hear you.
We cannot hear you properly, Yushe. Can you maybe turn up your volume or something?
How about now?
Yes, this is much better.
Yeah, thank you. Yeah, so I have a question. Is kind of follow up the discussion between Chris and Rob. So as you guys mentioned, like model-based, like a method for manipulation or learning data-driven method for manipulation. For some tasks, as Robert mentioned, they're kind of very complex. We even don't know how to represent. Maybe data-driven is a good way to do that. But generally speaking, a lot of tasks I see people either use data-driven method or model-driven method. I wonder, Rob, can you mention, can you comment in what kind of application maybe we prefer using model-driven method to deal with, and in what other applications maybe data-driven method is a good option to do that? Yeah, can you comment about that?
Yeah, I think I hinted earlier that I believe if you're moving around rigid bodies, then models probably work real well. And if you're dealing with amorphous, flexible, dynamic materials, then data-driven might make sense. But one thing that I heard a number of times in the talks today, because I really resonate with it, is the pain of calibration and registration. And it takes forever to do it right. And then you have to redo it because it drifts. Boy, is that a candidate for data-driven. If I can just find some clever way to do that registration between the vision and the kinematics and the tactile without, my student disappearing for 3 weeks of excruciating work, that's dynamite. And there's probably a continuum there from, super precise, well-designed systems where the registration isn't hard or it's only a small correction, up through systems where you can't have a model. So there is no registration. It's all, machine driven and then machine learning driven. And then in between, there's probably a huge range. And that may be a nice progression for us as a field that I'm impressed by, for instance, Peter Allen's work where he's getting 98%, graph success. Which is about the highest I've seen in a realistic set of models. So there's probably this big range where you can get better than that. You can get to the 99.99% reliability you're going to need for a kitchen robot by mostly using models and partly using machine learning along the way. But that's a very open question.
Thank you. Thank you.
So this meeting or workshop was entitled Soft X Applied to A, B, and C. And philosophically, soft is a rejection of the Industrial Revolution, which was all about precision. So, maybe the implication is we've got to think differently rather than go for precision. If you look at what went on in vision, what they did is they believed in precision. They would have cameras, they'd look at the scene, they'd figure out where everything was, and then they'd shut down their vision system, move the robot arm, do the graphs and everything else. And, they were shocked when the robot would miss. I don't know, I looked at that and said, what about feedback control? And, there's a lot of stuff in our community which, doesn't do the simple things. And I also think we have to, I think we should force students to deal with situations where there is no precision and make them think really hard about what the robust way to do the behavior is.
Let me see if there is a question here.
Any questions from the audience? Mohsen?
Yeah, I think there is no question from audience.
Oh, there is actually. Tariq, I hope I'm pronouncing your name correctly. Please feel free to unmute yourself.
Yeah, hey, hello, my name is Tarek. So I want to go back to the discussion of learning data-driven models for tactile perception and tactile control. There was a like small discussion about lack of standard data sets as they do like in computer vision. And one of the like success of computer vision, I guess, is to be able to create synthetic data, right? You can create millions of data in simulation, do domain randomization, and successfully transfer these models to real world. But unfortunately, this is not the case for tactile manipulation or tactile perception. So I guess my question is, do you see a feature of sim-to-real for learning for tactile perception and control, or should we stick to the real world and just work on the like sample efficient algorithms, which works with like a handful of data instead of doing extensive domain randomization and in simulation, and try to transfer these models to the real world?
I mean, I guess my thought is the latter. It sounds.
May I tell you one thing? If we just could align the data from the different types of sensors, things would be great. I mean, I saw so many different technologies today. There was a presentation from Catherine. They use boundary methods to compute the contacts. Other use taxels like we do. Other use images, and you have geometric transformations in between. So it would be just great to be capable of making the tactile data compatible. And so that would be a great achievement before arriving to have common machines. I mean, learning machine for learning and so on. I think that would be already a great achievement.
But there is another thing here when it comes to the tactile. The information we will get it from tactile depends on the action, right? So this is basically make it very difficult to simulate the tactile information, tactile data, right? But when it comes to the vision, it's not like that.
So maybe the visual tactile sensors might be the solution here then. Like if you think about it, it's like you're saying it's easier to simulate vision in simulation, and we have visual tactile sensors and then like contact sensors, right? So if we try to simulate vision-based sensors like gel side sensors, I think there's been like some recent work on that where they simulate vision-based sensors. Maybe that's the way to go.
Salvatore, please.
Yes, I want to add a comment on this aspect, in the sense that we work on tactile sensors, but a lot of things, the question is, which are the signals that a user of our tactile sensor wants? Do you prefer a tactile map, for example, to train artificial intelligence? Or do you prefer forces, torques, contact points? I noted that in a lot of presentation there are a lot of people that works on tactile sensors, like myself, and based on the task, in some case we elaborate the tactile map to reconstruct the forces, probably when the application is model based. In other case, we use directly the tactile map with the machine learning approach. In our in other presentation, other people use images and all the algorithms typical from computer vision. I work on technology, and my question is not only what is the killing application, but also before to find the killing application, which can be the signals that can be useful for to make all tactile sensors compatible? This is obviously an open question. Thank you.
And the other thing is, when it comes to the simulation, consider the fingertip. It's not only the tactile, which is basically connected to the certain actions. We have to consider also the physics of the finger and material, right? So this is very difficult to simulate it. I think Carmel can put a better comment here, right?
No, it is. I mean, I think there's been a lot of really nice progress on kind of reduced dimensional approaches to finite element modeling. But yeah, I mean, anytime you're dealing with these soft continuous systems, I mean, it comes down to solving a system of PDEs, right? And that can be computationally difficult. But no, I think there's been nice kind of work, on the FEA front. And then also, I've been working with folks looking at approaches using discrete differential geometry. And that's also been a very powerful tool that's popular in the computer graphics and entertainment industry, but more and more those simulation tools are becoming very accurate for actually modeling physics. So we've been using that a little bit also with these soft robotic systems.
Okay. Any last questions from the audience? Okay. If